Hi. In this section 2.6, we're going to talk about a couple different tricks for doing um, substitutions and transformations, which can help us solve a few more types of first order differential equations than the ones that we've seen. So what we've seen so far are a few special cases of first order differential equations. So in particular, these are the kinds that we've seen. Um, we saw separable in section 2.2, linear equations in 2.3, and exact ones in 2.4. And while those categories cover a lot of equations that you'll see in real life, it certainly doesn't cover everything. And beyond those, the groups that you can find solutions to kind of get smaller and smaller. But something that we find is that the tricks that you can use, that we used, that we learned in those sections, can sometimes be used with some modifications to cover a broader class of equations. So I'm skipping section 2.5, but it is sort of a trick of finding a different type of integrating factor, sort of like we used in section 2.3. So you can go and read that if you're interested. I'm skipping that, but I am going to cover 2.6, which is just some other. I want you to see an example of how you can do these substitutions because we'll see them in some other cases in later chapters. So to do this, I'm going to go through basically just two examples and show how we can use these substitutions to turn an equation that's not necessarily in one of the forms that we've seen before, and we can turn that equation into something that looks like, something from 2.2, 2.3, or 2.4. Our first example is called Bernoulli Equations, and it takes this form here where we have our first derivative by itself, and then we have these two kind of coefficients that only have x's in them, and these need to be continuous on an interval a to b, and we want them to multiply. One term can have just a y in it, and then the other one can have a power of y in it, and that power can be any real number. Okay, so let's suppose that we have an equation that can be put into this form. So this doesn't look like any of the examples or any of the categories that we saw before, separable or linear or exact. It's not linear because, in particular, because you have this y to the n term. Um, although if n equals 0 or n equals 1, then it is linear. So we'll kind of assume that n is not 0 or 1. Okay, so that's what I just said. I just wrote down what I just said. And then so we're going to assume that n is not 0 or 1, and we're going to make a substitution. So let's let v, a new variable v, equal y to the 1 minus n. And so we're going to rewrite this equation. So instead of having y's in it, it will now have v's, and v is going to be the equation that we want to solve. And so if we're going to have v's in it, we need to know something about what the derivatives of v are going to look like with respect to x. X is still going to be our integrating variable or our derivative variable, blah, blah, blah. So then by the chain rule, what is the derivative of v with respect to x? Well, v is a function of y and y is a function of x, and that's why chain rule applies here. So to take the derivative of v, you take the derivative, or you take the derivative of v with respect to x. First, you take the derivative with respect to y, and then multiply that by the derivative of y with respect to x. Okay? And because this is our definition of v, dv dy is going to be, you just use the power rule, take our 1 minus n down, y to the 1 minus n minus 1, which is negative n, and then multiply that by dy dx, whatever dy dx is. All right, now I should have given this equation a name, so I will call it star now. And next what we're going to do is divide our original equation star by y to the n and substitute in v and dv dx. And what we will get is, so first let's do that division, and we get 1 over y to the n dy dx plus y divided by y to the n is y to the 1 minus n p of x equals q of x. Okay, so that's from this step right here. And then this part here, 1 over y to the n, or y to the negative n times dy dx, is the same as this here. So we can replace that with 1 over 1 minus n times dv dx, right? I just sort of divided that over to this side. Okay, so that's that first term. And then this thing is exactly our definition of v. So that's the substitution that we're making. So our second term is going to be v times p of x. And I'm not worried about getting rid of p of x or changing it because it doesn't have any y's in it. What we want to do is get rid of all the y's and turn them into v's. And then same with q of x. Okay, so that is our new equation, and this is the second line here is where I did the substitution of v. Okay, so what's nice here is that this new equation is linear in v. And so, and you can tell that because you just have your dv dx here and you have your v here, and you don't have any sort of nonlinearities in v the way that you had your nonlinearity in y in the original equation. And so we can solve with the method from section, what was it, 2.3. Okay, so we know how to solve it. And I'm not going to solve it here because I have an entire video about how to solve it before. So that's the whole point, is that we did a substitution that got a nonlinear equation and turned it linear so that we can do the solution. And when you find your solution, it's going to be in v, but then you just sort of back substitute in what y is to get your final answer in y. All right, so that's one example. Now I'll do another example of another kind of substitution. All right, so our next example are called homogeneous equations, which is not necessarily the same concept as homogeneous that we talked about really early in chapter 1. Don't worry about that. So if you've got an equation of the form dy dx equals some function of x and y, the first order equation, if the right-hand side, all the stuff without the derivative in it, if that can be shuffled around to look so where everything can be sort of written in terms of a y over x, then you've got a really obvious substitution. So let's just do an example. So an example in your example. So the equation we're going to use is xy plus y squared plus x squared dx minus x squared dy equals 0. So as an aside, if we were just given this problem like in the homework and said solve it, then you would probably want to check first to see if it was separable or linear, or exact. So you can tell right away that it's not linear because it's got a y squared term. Um, and separable, you can basically see that same way too, because if you tried to get all the x's and y's on separate sides of the equal sign, you'd have to be dividing by y's and blah blah blah. I mean, you can try shuffling around. So let's check. The really obvious guess would be that this is exact because this is written in this dy, like an mdx minus ndy form. But remember the test for exactness. So we take the dm dy, which would equal x plus 2y plus 0. So I guess I don't need to write that. And then right here we have our dn dx, which is equal to negative 2x. And so you can see these things are not equal, so this is not exact. Okay, so we have that this equation doesn't fall into any of our other cases. Okay, so now we're going to see that it is in fact a homogeneous equation, and then we'll see the substitution that we could try to do. So let's rewrite this into our sort of regular derivative form with the dy dx in it. So first, I'll just get the dy, I'll add the dy term over, and then I want to get dy dx by itself. And so I get something like this, xy plus y squared plus x squared, all divided by x squared. And if I do this division out term by term, what I'm left with is y over x plus y over x quantity squared plus 1. And so this is what I meant earlier when I said, you know, if to have a homogeneous function, we need it to be able to be expressed as a function of y over x, and we have that here, that everything has this y over x thing here. So what we're going to do is a substitution, and this is the trick. So we'll make the pretty obvious substitution. V equals y over x. Okay, so we need to know. So we can plug these in for the y over x, but then we also need to get rid of this dy dx. So we need to know what dy dx equals in terms of v. And there are a couple different ways that you can do this. You can do it straight off doing product rule, or sorry, quotient rule on here. It's going to be a little bit simpler if we rewrite this as y equals vx. That gets rid of our quotient rule because what we want to figure out is what does dy dx equal in terms of v's. And so if we just get y by itself, then we can do that directly. So then we can take the derivative with respect to x on both sides, and we get dy dx, we can use product rule now instead, equals dv dx times x, we'll leave the second term alone, plus v times the derivative of x, which is just 1. So now we can actually substitute that back into the equation at the top, and what we get is dv dx x plus v equals, now we'll substitute our v into that right-hand side over there, and we get v plus v squared plus 1. And if we simplify, we get those v's cancel out, and we get dv dx equals v squared plus 1 over x. Now we're in good shape because this is actually separable, right? So we get 1 over v squared plus 1 dv equals 1 over x dx. We can put all these on one side and all the x's on the other side, and then we can integrate. And these are pretty easy. The left-hand side might not look easy, but then if you remember that it is in fact arctan of v, and then on the right-hand side, this is just ln of x, and we get our constant, just one constant for both sides. So we can actually go through and solve this for v just by taking the tangent of both sides. So get some more room. We get v equals the tangent of the whole quantity ln of x plus c, simply c. There we go. And now we actually want our answer. We're looking for y. We're not looking for v. But that's okay because we have our substitution. We just substitute it back. So v equals y over x equals, and then that equals tan of all this stuff. And now we can solve for y just by multiplying the x over, get x tangent ln of x plus a constant. And that is our final answer. So the point here was being able to find a substitution that turned our differential equation into a simpler equation that we have a trick to solve. So we knew another trick to be able to solve that simpler equation. And then we back substituted to get our final answer in terms of y, which is the thing that we wanted from the beginning. So what we've seen in this video is just a couple other tricks to where we could take an equation that was not one of the categories that we saw in the beginning of the chapter and turn it into one of those categories so that we could use those other tricks to be able to solve it. And so this is the end of chapter 2, or at least of what we're covering in chapter 2. And what we've seen is first order equations and some ways that we are able to solve them. And soon we'll be going on to second order equations and seeing that we can use some of these tricks, but they actually get a little bit more complicated. So we'll spend a lot of time on second order equations. But what we're going to do before we move on to second order equations is a couple sections in chapter 3 where we see how we can use differential equations to model real world situations, and then use the tools that we've seen for first order equations to actually solve those. And then we'll jump on to second order equations. So that's the end of this video, and our next videos are going to be on chapter 3.